He is an assistant professor and also the director of the Hydrologic Modeling and Assimilation Lab in the Department of Civil and Environmental Engineering at Portland State University. So we have the pleasure of actually collaborating with him on a project funded by DOE. I think the project just started about a year ago. Peyman is going to tell us about it. So he has a lot of expertise and experience in data simulation. So it's really great to see this particular project also using machine learning to look into data simulation as well. So with that, take it away, Peyman.
Thanks so much, Ruby, for the introduction. So as you see, this is the title of my presentation for today, toward integrating E3SM with machine learning enhanced data assimilation for improved Earth system predictability. So I'm gonna start my talk with this slide. Basically summarizes the hydrologic predictions versus observations. So on the left-hand side, this schematic shows the hydrologic model. And as all we know, in order to be able to derive a hydrology model, we need atmospheric forcing data. We have the model parameters and state variables within the model. And then basically we run our hydrology model and we get model predictions. But we know that the model predictions are not accurate and reliable because of some reasons. The first one, I listed 4 of them here, because of the limitation of measurements and basically spatiotemporal representativeness of the data. And for example, the forcing data, or conceptualization of the model and non-uniqueness of parameters, basically the uncertainty associated with the model parameters. The first one, uncertainty associated with the atmospheric forcing data that we use to derive the hydrology model. Imperfect representation of a real system. We know that the hydrology model or any land surface model is just a simplified version of a real system. So it's not a perfect system. And this is more of a related to the model structural uncertainty. And last but not least, it's initial and boundary condition uncertainty. So on the right-hand side, you see the observational data. So we have observational data in either from the in-situ measurements, from satellites, and we know that the observational data also is not perfect, because of if you use the satellite data, we know that because of the satellite retrieval error, again, the observational data may not be as accurate as what we expect. So in situ measurement error and error in documenting and archiving data. So what data assimilation does, basically data assimilation tries to bridge these two components, the hydrologic model predictions and observations. So by definition, data assimilation is defined as a set of statistical techniques that enable us to improve the knowledge of the past, present, or future system state and or parameters, depending on how we define the data assimilation configuration, jointly using experimental data and theoretical knowledge on the system. So if you look at this visualization here, I really like this visualization. So as you see, we have our dynamical model. Here in our case is a hydrology model, land surface model, but it can be any dynamical model. And basically we use a sort of data set. Here we have the forcing data, meteorological forcing data to derive the hydrology model, land surface model. And then when we go from, for example, when we do the simulation, we go from step t to t+1, and then we try to see if the observational data is available at that time step. And then, as you see, observational data here, we have it from satellite or in situ measurements, and then we assimilate it into the model, and then we update the model state and parameters at that time step, and then modify the restart file or the initial condition of the system and run the model again from t+1 to t+2, and then we do this process again and again. This is more of a sequential data assimilation process. So in variational data assimilation, it's a little bit different. but in sequential data assimilation, basically we run the model step by step, and then depending on the availability of the observational data, we do the data assimilation. If we don't have observational data, basically we don't do anything. We just run the model probabilistically, and we rely on the initialization of the system itself. So I have another slide here. I usually use this slide to describe the difference between the hydrology model and hydrology model with data assimilation. On the first row, as you see, we have our watershed. We have, based on the conceptualization of the system, we have a hydrology model, and then assuming that we are not using data assimilation in the prediction phase, we use historical data, observational data to basically calibrate our model parameters. And then in the forecasting phase, we use the calibrated model parameters. If we want to do the probabilistic simulation, we can perturb the calibrated model parameters, and we have the initialization of the system, and we run the model forward. But we know in reality, so this watershed or the land surface is being observed by different satellites. So in hydrologic data assimilation, basically we say that why don't we use the satellite observational data, which is kind of available, to basically improve our modeling skill. So then, as you see in the second row, in the prediction phase, so it's not, the model is not running deterministically, it's a probabilistic simulation. So we start from a initialization, which is S. We have theta here, which is the model parameters. And then we run the model from T to T+1, and then we see if we have the observational data at time step, and we assimilate it into the model. We update the model parameters and state variables at that time step, and then we run the model again from T+1 to T+2, and we do this process over and over again, all the way to, let's say, today. And then we use the last the last updated version of this restart file, or the initialization of the system that we have, S+1 here and theta plus here, which is the posterior estimates of model parameters and state variables to run the model in the forecasting phase. So we, in the forecasting phase here, we say that we are relying on the most accurate and reliable initial condition of the system for the forecasting. And also we are using the posterior estimates of the parameters. So this slide, this is the same slide that I showed you guys in the E3SM all hands meeting. So speaking of data assimilation, we have two important components here that we have to highlight: the nonlinearity of the system and dimensionality of the system. So ensemble-Kalman filters basically are known to be one of the kind of widely used DA techniques in hydrologic community and land surface modeling community. And the reason is it's the implementation is very straightforward, and basically it doesn't need that much knowledge kind of in statistics. You can basically read a few textbook or look at the codes which are already available to start coupling ENKF or ensemble-Kalman filter with any dynamical model. So the implementation is very straightforward. This is one of the reasons that people usually use this approach, and it's very effective, and it has been extensively used in many studies. But we know the ensemble-Kalman filters is a good fit for the systems with higher dimensions. So, but ENKF, we know that ensemble-Kalman filter-based data assimilation techniques has some inherent features which result in suboptimal performance. So I included three of them here. So the first one is the Gaussian assumption of the error. The way that we assume the errors distribution, it's Gaussian, and the linear updating rule within the ENKF. If you ever use the ENKF, you know that you calculate an innovative term and you multiply it to a Kalman gain, and you basically calculate the posterior value of the parameters on the state variable. And the last but not least, which is the most important one, is the violation of the water balance, that we have to make sure this shouldn't happen, because this is a hydrology. We shouldn't add water to the system, and we shouldn't remove the water from the system. So we have to follow the physics. So because of, in order to fill these gaps, so we use particle filters. But as you see, particle filters, they could fit for dynamical models, highly nonlinear dynamical models. But when you want to use it for the systems with higher dimensions, it's not like as effective as the ensemble Kalman filters. So basically, we have multi-scale problems. So for example, ELM or E3SM is a multi-scale model, which means it's highly nonlinear model, and it's high dimensional system. So we have to make sure we use a methodology which is a good fit for such system. So a little bit background about the methods. So the first paper, as you see on the top left corner, hydrologic data assimilation with ensemble Kalman filter. This paper published by Rolf Reichley, Dennis McLaughlin, and Darren Cobby from MIT in 2001. This is basically the kind of first paper which published on has been published on hydrologic data assimilation with ensemble Kalman filter. And 5-6 years after that, the second paper on certainty assessment of the hydrologic model state and parameter sequential data assimilation using particle filter, published by Hamid, Hoshin, and Srush from UCI. And this goes back to exactly 20 years ago. And basically, in this paper, the authors tried to fill those three gaps in ENKF-based data assimilation techniques. And later in 2018, we realized that this particle filtering based data assimilation techniques are great for highly nonlinear system, but when we want to use them for hydrologic models with higher dimensions, so the model is not as stable as the ENKF methods. Then we tried to incorporate a machine learning module along with coupled with a Markov chain Monte Carlo approach into this particle filtering method to basically come up with a methodology which is a kind of a sort of a good fit for a higher dimension and highly nonlinear dynamical systems. So this schematic here basically summarizes the machine learning enhanced data assimilation techniques. We call evolutionary DA. The reason that we call it evolutionary DA, because we use the crossover and mutation operators of the genetic algorithm when we want to resample the particles along with MCMC to basically generate the most informative prior distribution, because the more informative prior distribution, we can say the more informative posterior distribution, or more accurate and reliable posterior distribution. So the prior knowledge is very important. So if I want to go into the detail a little bit, I don't want to go into the equations, but the first two equations, as you see here, the first one is the model operator, the second one is the observation operator. We use these two equations basically to describe a dynamical system. Here is a hydrology model. X is the state variable of the system. The U is the atmospheric forcing, and theta is the forcing data. So, and basically what we do here, this is, we calculate the, basically we are interested in calculating the posterior estimates of the state variable and model parameters times the t given the observational data. So this is the conditional probability. So as we said, this observational data is available from satellites, in situ measurements, and we want to update these two variables here, state variable and parameter here, given this observational data. So, and then we use the Bayes law. So basically we multiply the likelihood by prior distribution, and we divide it by a normalization factor. This is basically the Bayes law. So as you see, we have the prior distribution here, multiplied to likelihood, we divide it by marginalization factor, and we calculate the posterior. So basically, the particle filtering-based data assimilation relies on this equation. So, and then in order to be able to calculate likelihood, we assume a Gaussian distribution, and then we use this equation. So, but one of the most important aspect of this methodology is that in order to, one of the problems with the particle filtering based data assimilation technique is that it basically is the sample impoverishment and particle degeneracy problem. So basically, the model tries to put the significant weight or the importance to one of the particles as you run the model forward, and then model kind of converged to one, I would say, solution, and sometimes that solution is not correct, and then you don't have any predictive interval from your probabilistic simulation, and then it's kind of useless. So we have to make sure to kind of increase the diversity of the particles during the sequential filtering process. So that's why we use the mutation and crossover operators of the genetic algorithm. This is exactly what's happening within the GA method. Basically, we use these two operators to combine the chromosomes and generate new offsprings, and we say that new offsprings are better than the those, let's say, parent particles or chromosomes that you use to combine, and you generate more informative or better chromosomes. So we inspired from that evolutionary process within the GA to improve or increase the diversity of particles. But one of the problems that we have here, because we don't basically do any optimization here, we just use these two operators, we have to make sure the new particles that we generate at each time step they are reliable enough to be used for the next step. So then we use the MCMC approach. As you see here, we calculate the metropolis testing ratio to accept or reject the new generated particles. Let's say if a new generated particle is a good one, we accept it, and we move it to the next step. But if it's not good, we reject it, and we use the particle which is already available from the previous step. So, and this flow chart here basically shows how the GA-MCMC method is kind of implemented or performed within the particle filtering method. So from this evolutionary DA, we can provide and generate more informative prior and better estimation of the prior distribution. It minimizes the particle degeneracy and sample impoverishment, which are the main problems within the particle filtering DA. So it's all ensemble size can be sufficient to set up the DA. So we don't need to go after large ensemble members that usually PF-based DA methods they need. An effective DA method to be used within high-dimensional hydrologic and land surface models. So these are the important, let's say, advantages of this technique. So this is one of the examples I just wanted to highlight how we use this method in other studies for drought predictability. So we basically, in this study, we use NOAA-MP land surface model. We used soil moisture data from SMOPS and the ET from MODIS, and then we kind of assimilated these two observational data into the NOAA-MP land surface model, and we generated posterior estimates of the soil moisture and ET, and we use that posterior estimates to calculate drought index for drought monitoring. So, for example, we used our product here to see to what extent it's good compared to the USDM drought map, as you see here. So here, this slide shows the how drought map could capture the footprint of the extreme rainfall of Hurricane Michael. So Hurricane Michael made a landfall in 2018 in southeast US here in this region and made landfall on October 7. So, but when we look at this, the drought map from the USDM, we see that you can see how the droughts evolve over time. So basically, the hurricane made a landfall and in a few days after October 2nd here. But when we look at the drought index that we calculated based on the posterior estimates of the ET and soil moisture, or based on DA, we see that this drought map generated from hydrologic data assimilation system, it says that the region is drought free in that week, but the USDM is still showing some drought across the region, which is not correct. That we know that the hurricane and the extreme rainfall made a landfall in a few days after October 2nd, 2018. So, and it's drought free. So so we were doing such analysis just to make sure to what extent the drought map generated by this hydrologic data assimilation system is consistent with the reality and what really happened over that region at that week. So, and then what we did, this is just an example. On the left-hand side, you see the drought monitoring, integrated drought monitoring system based on the NOAA land data assimilation system. So on the right-hand side, you see the USDM drought maps, United States drought monitoring for over the year of 2020. So we were kind of comparing these two, and we were trying to study and see to what extent we were able to provide accurate drought maps for the United States. So, and we also look at the predictability of drought at 1 month, 3 months, and 6 months lead time. So the orange color, the line with orange color here shows the basically the drought index that we calculated at 6 months and 3 months and 1 month lead time, and we compare it with the SPI and SSMI drought indices available from observational data, just to ensure that the calculated index is reliable enough to be used for drought monitoring. So this slide is also showing the how. So here in this study, we coupled hydrodynamic least flood to the hydrodynamic model with the particle filter, the machine learning enhanced ML data assimilation technique. And here I'm just trying to see how the model parameters, this is channel roughness, this is the bathymetry. I'm just trying to show you how the model parameters evolve over time and then converge to the right solution. This is a synthetic study. Usually when we want to couple a DA method with a new dynamical system, we do a synthetic experiment just to make sure that the model parameters are able to converge to the right solution. As you see here, from 0 to 40 days, you see how the model parameters converge to the right solution, and bathymetry as well. So, so again, for this project that we are currently working on, we are doing exactly the same analysis. So here, this is the same slide that I showed you guys in the E3SM lands meeting. So we are integrating E3SM land model with a state-of-the-art data assimilation technique, and we are trying to assimilate satellite observation into ELM to improve E3SM predictability while accounting for uncertainties. So we know that data assimilation is expected to provide more accurate and reliable initial condition for the ELM by integrating observations such as soil moisture, snow, and vegetation related to state variables into model while accounting for uncertainties. And as a result, the improved initialization can translate into enhanced E3SM predictability, particularly on S2D timescales, where land model play a crucial role. So this is basically why we are working on this project. So soil moisture impacts and SWE, the importance of these two variables have been widely highlighted in E3SM all hands meeting. But we know that if we can improve the predictability of these land surface processes, we know that they are heavily impacting the atmospheric condition and their interaction with the atmospheric processes. We can expect that we can improve the E3SM S2D predictions. So objectives. So assimilating snow-related variables into ELM to improve accuracy and reliability of SWE predictions, along with other snow properties, including snow cover fraction and snow depth. We know that this is one of the problems within the model, so we try to basically fill this gap using the data assimilation and assimilating glass, LAI, and SNAP soil moisture into the model to improve the land atmosphere feedback in E3SM and therefore improve the drought predictability over the Great Plain. So let me wrap up my presentation. I have only 2-3 minutes. So we are using the methodology proposed in Ripley et al. To perturb the forcing data, and then now this is the same slide that I showed at the E3SM all-hands meeting. So we basically run the model probabilistically right now, but it seems that when we look at the predictive interval from the ensemble simulation, we see that it's kind of even the 95% predictive interval is far from the observation, and it shows that we have to also focus on the model parameters and initialization of the system. We add white noise to them, to initialization of the system, and sample the parameters and consider all the uncertainties associated with different layers of the model simulation to be able to capture this observational data and then move on data assimilation. So we identified the model parameters related to soil moisture and ET already, and we are currently using the LAC and HyperQ sampling to basically sample parameters. And for the snow SWE, we identified a few parameters here, as you see in this table. We are still in the process of studying other snow albedo-related parameters. As you see from this paper, snow albedo plays a big role in, as you see, identified as a contributing factor to model biases in simulating surface albedo and snowpack evolution. So we are still in the process of studying kind of what parameters we have to consider within the data assimilation system. So we already identified these parameters, but as soon as we finalize the parameters, we will focus on doing the sampling and running the model probabilistically. And after getting that knowledge, we will focus on developing the coupling, the DA coupling. So it's 30 minutes. I think I'm done. Thank you so much for your attention, and I'll stop here and I take comments and questions.